The next question is, if A is equal to I0, 0I, then find A square. So this is also a very, very important problem given many times in the examinations. So given that matrix A is equal to I0, 0I. Now we have to find A square. A square is nothing but matrix A into A. Remember carefully. So now which is equal to here matrix A is I0, 0I, and again the same matrix you have to multiply with the same matrix I0, 0I. So then we get here, see observe here, first row and first column multiplying here I into I plus 0 into 0, 0 into 0. First row, second column. So I into 0, this is first row, second column, plus 0 into I, 0 into I, first row, second column. Now second row, first column you have to write here. So second row, first column, 0 into I, second row, first column, 0 into I, plus I into 0. Now second row, second column multiplying 0 into 0 plus I into I. So now A square is equal to, we get, see here A square, therefore A square is equal to, so here I into I square plus 0, this is I square plus 0, and here 0 plus 0, 0 plus 0, and here 0 plus 0, 0 plus 0, and here 0 plus I square, 0 plus I square. Now we get A square is equal to, here I square, 0, 0, I square. See, we know that, remember that I square value is considered as minus 1. Wherever I square is there, replace that is by minus 1, 0, 0, minus 1. And also further you can write, this is also minus of 1, 0, 0, 1. See, we know that, so identity matrix of order 2, I2 is equal to 1, 0, 0, 1. We know that. So that's why here, this 1, 0, 0, 1 is replaced by unit matrix I. So finally we get A square is equal to minus I. Like this, we can find the square of the given matrix, that is A square. The next question, if omega is complex, that means non-real roots, complex cube root of unity, then show that determinant of 1 omega omega square, omega omega square 1, omega square 1 omega is equal to 0. See what is given here, very, very important problem. This is many times repeated in the examinations. So given that, see omega, this is called omega. Omega is complex cube root of unity. Omega is complex cube root of unity, means that is the sum of 1 omega omega square is equal to 0, and also the product of 1 omega omega square we get, that is omega cube is equal to 1. These conditions applicable. Now what I am taking is here, so given that the LHSs I am considering, what is the determinant of 1 omega omega square? So next omega omega square 1 omega square 1 omega. I am considering this is. Now what I am doing is here, either see here R1 to R1 plus R2 plus R3, applying the row operation. So R1, this is R1, this is R2, here this is R3 elements, no? So now adding R1, R2, R3, writing in the place of R1. So that means what? 1 omega, omega square adding and writing in the place of R1. Again omega, omega square, 1 adding and writing in the place of R1. Again omega square, 1 omega adding and writing in the place of R1. R2 and R3 rows are remain same. No change in the R2 and R3. Just adding R1, R2, R3 and writing in the place of R1. So now what happens here? Observe that. See, already if you observe that, so here in the first row 1 plus omega square, here also 1 plus omega square, 1 plus omega square, all the three elements. See, already we have the condition here, 1 plus omega square is equal to 0. So that's why here, so which is replaced by, this is replaced by the first row elements, replaced by here 0, here 0, here 0 as per the given condition. Now second row is as it is omega square 1, and third row is also no change, omega square 1 omega. See, observe here. So determinant of that 3 by 3 matrix, so all the elements are in the first row 0 only. So that's why in a square matrix, any row or column, all the elements are equal to 0 here. So we know that a property in a square matrix, any row or column, elements are equal to 0, then its determinant is equal to 0. Its determinant is also equal to 0. This is a property of the determinants. So as per that, so we can write determinant of this is 0 only. See, which is the RHS. So therefore LHS is equal to RHS. So like this we can prove the given matrix determinant is equal to 0 if omega is the complex cube root of unity. The next question is, define symmetric matrix if A is equal to -1, 2, 3, 2, 5, 6, 3x7 is a symmetric matrix, then find the value of x. Now here, definition of the symmetric matrix I am writing here. How can we define symmetric matrix? A square matrix capital A is said to be a symmetric matrix if A transpose of A is equal to A. Transpose of A is equal to same matrix, then we can say that the given matrix is a symmetric matrix. So here, given the matrix A is equal to, given that matrix A is equal to, so -1, 2, 3, 2, 5, 6, 3, x7. So since capital A is a symmetric, capital A is a symmetric, capital A is a symmetric matrix, capital A is a symmetric matrix. So when capital A is a symmetric matrix, so then the conditions which are applicable here, so which implies, so A12 element is equal to A21, A23 element is also is equal to A32 element, and so A13 element which is also is equal to A31 element. So 1 2 element means what? First row second column element, that is 2. So 2 1 element is what? Second row first column element. See here, observe both are same only. And similarly here A13 means first row third column element, so that is 3 is equal to third row, 3 1 means third row first column element, both are same only. So now to find the value of x here, so now second row first column element here, since to find x, so second row third column element 2 3 is equal to, so third row second column element, so third row second column element. See, second row third column element is what here? 6. So 6 is equal to third row second column element. This is third row 3x7. Second column, that element is x. So third row second column element is x. So therefore x is equal to 6. Like this, in a simple way, we can find the missing value if the given matrix is a symmetric matrix. By using these conditions, we can find the value of the required. See here, the next question is define trace of a matrix and find the trace of capital A if matrix A is equal to 1 2 minus 1 by 2, 0 minus 1 2, minus 1 by 2 2 1. So what is trace of a matrix? The definition of trace of a matrix I am writing here. See, suppose let capital A be a square matrix. Capital A be a square matrix. Then the sum of the principal diagonal elements, the sum of the principal diagonal elements in a square matrix, the matrix A is a square matrix, no? So in a matrix A, capital A is, we have taken a square matrix, then the sum of the principal diagonal elements in a matrix A is called trace of matrix A, right? So now it is denoted by so TR of A. See, the sum of let capital A be a square matrix, then the sum of the principal diagonal elements in a matrix A is called trace of a matrix A. It is denoted by TR of A. Now here we have to find the trace of the given matrix. So how to find the trace of the given matrix? Here given that matrix A is equal to 1 2 minus 1 by 2 and 0 minus 1 2 and here minus 1 by 2 2 1. See, the principal diagonal elements, these are the principal diagonal, this is the principal diagonal. This is called what? Principal diagonal for your understanding. Principal diagonal. So the sum of the principal diagonal elements. So that means so trace of A is equal to so 1 plus minus 1 plus 1 which is equal to 1 plus into minus is minus 1, so plus 1, so these two are gets cancelled. So now trace of A is equal to 1. So like this we can define the trace and also we can find the trace of the given square matrix. See in the next question, find the rank of the matrix 1, 2, 3, 2, 3, 4, 0, 1, 2. So now you take the given matrix capital A is equal to 1, 2, 3, 2, 3, 4, 0, 1, 2. So now to find the rank of 3 by 3 matrix, its order is what? 3 by 3. Now find the det A is equal to find the rank of the given 3 by 3 matrix, find the determinant of given matrix. So that is 1, 2, 3, 2, 3, 4, 0, 1, 2. So now find the determinant of this is 1 into 1 presenting row, column deleted. So we get 3, 4, 1, 2 determinant of. So second element is taking with a minus 2 into, so 2 presenting column, row deleted. So 2, 4, 0, 2, and again last element is taking with 3 plus 3 into 3 presenting row, that is first row, last column deleted. So we have 2, 3, 0, 1. So now which is equal to 1 into, so this is 6 minus 4 and minus 2 into, this is 4 minus 0, like this only we have to multiply, no? So plus 3 into, so this is 2 minus 0. So now what we get, see here, 1 into 2 and here minus 2 into 4 and plus 3 into 2, so which is equal to, so 2 minus 8 plus 6. So these two are gets cancelled, everything plus 8 minus 8 is equal to 0. See determinant of 3 by 3 matrix, if you get 0 to find the rank of that matrix, so now consider any 2 by 2 matrix of A. Consider any 2 by 2 matrix of A. When it is, if you get the determinant of 3 by 3 is 0. Suppose 3 by 3 matrix determinant is not is equal to 0, straight away you can write the rank is 3 only. Why? Because order of this matrix is 3, so that's why you can write rank of that matrix is 3. But here we get determinant is 0, then you have to consider any 2 by 2 matrix of A, any 2 by 2 submatrix. Here, any 2 by 2 submatrix of A. Now considering let A is equal to here, I am considering here 1, 2, let B is equal to, already we have taken no matrix A, let B is equal to 1, 2, 2, 3, you consider. Anything you can consider 1, 2, 2, 3 or 2, 3, 3, 4 or 2, 3, 0, 1 or 3, 4, 1, 2, any 2 by 2 you can consider. So now find the determinant of B here. Determinant of B is equal to, we get 1, 2, 2, 3 determinant of, so which is equal to 3 minus 4 which is minus 1, so is equal to, is not is equal to 0. So determinant of B is equal to minus 1 which is not is equal to 0 means, so therefore matrix B is a non-singular matrix. Is a non-singular matrix of order 2. What is the order of the matrix B? 2 by 2 order. So that's why it is a square matrix of order 2. So that's why if it is a non-singular matrix, any 2 by 2 matrix of a given 3 by 3 matrix is non-singular, submatrix is non-singular. So therefore, even though the given matrix is 3 by 3, so now rank of A is equal to 2. Why? Because so the 2 by 2 submatrix of A is a non-singular. So whose order is 2? So that's why given matrix rank is also 2. So that's why like this we can find. See, next question is define triangular matrix. So how to define the triangular matrix? So the definition of triangular matrix. Triangular matrix. A square matrix, capital A is a square matrix, is said to be a triangular matrix, if it is either an upper triangular matrix, if it is either an upper triangular matrix or a lower triangular matrix. A lower triangular matrix. A square matrix, capital A is said to be a triangular matrix if it is either an upper triangular matrix or a lower triangular matrix. For example, so let A is equal to 1, 3, 1, here 3, 5, 0, 4, 6, 0, 0, 7. Suppose the matrix is like this. So which is called an upper triangular matrix. Why it is called an upper triangular matrix? The elements below the principal diagonal are equal to 0. See, this is the principal diagonal. Principal diagonal elements are 1, 4, 7. Below the principal diagonal elements are 0. So such matrix is called an upper triangular matrix. Similarly, for example, here this is example 1, or let A is equal to, suppose if you take 1, 0, 0, so 3, 4, 7, otherwise here also if you take 0, next here, so 5, 6, suppose if you take, and 8, like this. See, observe here, so the elements above the principal diagonal, are equal to 0, which is called a lower triangular matrix. Here, the elements above the principal diagonal elements are 0, that is called a lower triangular matrix. So, the elements below the principal diagonal are equal to 0, that matrix is called an upper triangular matrix. Like this we can define the triangular matrix. So in this video we are going to discuss matrices 2 marks, continuation, Vsaqs, previous year's questions, Question is, solve the following system of homogeneous equations. The equations are given like this: x minus y plus z is equal to 0, x plus 2y minus z is equal to 0, 2x plus y plus 3z is equal to 0. How to solve this homogeneous system of equations? Now, the equations are given here, given that x minus y plus z is equal to 0 and x plus 2y minus z is equal to 0, 2x plus y plus 3z is equal to 0. See the matrix form of the system. The matrix form of the system, homogeneous system this is so coefficient matrix capital A is equal to, see here 1 minus 1 1 and 1 2 minus 1, so 2 1 3, and here x is equal to the matrix x is x y z and the O matrix is here 0 0 0. See, this is a homogeneous system of equations. To find the solution of this, you have to find the determinant of coefficient matrix. That means det A is equal to, we have to find. So det A is equal to, we can write it as 1 minus 1 1 and 1 2 minus 1 and 2 1 3, right? Determinant of A is equal to. Now det A is equal to, see here 1 into, so 2 determinant of 2 minus 1 1 3, see 1 present in row and column deleted, 2 minus 1 1 3. Next second element we have to take here actually plus minus plus, so here taking with minus of minus 1 into determinant of minus 1 present in column, first row deleted, we get 1 minus 1 2 3, determinant of 1 minus 1 2 3, 1 minus 1 2 3, and last element is we have to take with plus 1 into last element present in row, that is first row, and last column deleted 1 2 2 1, so determinant of 1 2 2 1. So now finding the determinant of this is, so 1 into, so this is 6 and plus 1, so here plus 1 into here 3 and minus of minus 2, that is plus 2, and here plus 1 into, so 1 minus 2 into 2 is 4. Now here we get 1 into 7 and here 1 plus 1 into 5 and plus 1 into minus 3. So now what we get here, 7 plus 5 minus 3, which is equal to, we get 9. So determinant is not is equal to 0. If you get 9 means 9 is not is equal to 0. So that's why we can say that the system has the given homogeneous system has trivial solutions. This is called trivial solution. If the determinant is not is equal to 0, if we get. So the system has trivial solution. What is the solution of the system? The solution is x is equal to, y is equal to, z is equal to 0 only. X is 0, y is 0, z is 0. So like this we can find if the homogeneous system of equations are given, we can find the solution of that homogeneous system of equations. See in the next question, construct a 3 by 2 matrix whose elements are defined by Aij is equal to 1 by 2 into modulus of I minus 3j. here you remember that. So I represents the rows, J represents the columns. Now here we have to find the 3 by 2 matrix. Means what? 3 rows and 2 columns. So let a 3 by 2 matrix, I am considering here. Let a 3 by 2 matrix capital A is equal to, so here I am taking, so A11, that means first row, first column elements. So A12, first row, second column element. A21, second row, first column element. A22, second row, second column element. So A31, third row, first column element. A32, third row, second column element. See, observe here, this is a 3 by 2 matrix. So you have to consider a 3 by 2 matrix like this. See, first row, second row, third. Right? Now you have to find the elements are given like this here. So since Aij is equal to given 1 by 2 into modulus of I minus 3j, given like this. Right? Now A11 I am finding to find the 3 by 2 matrix. First row, first I represents 1, j represents 1 here. So that means I is equal to 1, j is equal to 1. Substituting in this 1 minus, so 3 into 1, so which is equal to 1 by 2 into modulus of 1 minus 3, that is minus 2, which is nothing but 1 by 2 into modulus of minus 2 is what? Plus 2. So which is equal to 2 gets cancelled 1. So similarly A12, first row, second column element I am finding. So here first row, first column element is what we get? 1. A11 is equal to 1. So A12, same condition considering 1 by 2 into modulus of, now I is equal to 1, j is equal to 2, 1 minus 3 into 2. So now we get 1 by 2 into, so here 1 minus 6. So this is 1 by 2 into modulus of minus 5, which is equal to modulus of minus 5 is plus 5 only. So that's why 5 into 1 by 2, 5 by 2. So now A12 element which is equal to, so 5 by 2. So keep aside. Now coming to the next element, so that is A21. So A21 is equal to, again same condition, in the same condition. So 1 by 2 into I represents 2 minus j represents 3. So that's why j represents here 1. So 3 into 1. So which is equal to 1 by 2 into 2 minus 3. So which is equal to 1 by 2 into modulus of minus 1. So which is equal to modulus of minus 1 is plus 1. So that's why second row, first column element is equal to 1 by 2. So now second row, second column element A22. So which is equal to, so same condition taking I is equal to 2, j is equal to also 2. So in this substituting, so we get 2 minus 3 into 2. So which is equal to 1 by 2 into, so 2 minus 6. So which is equal to 1 by 2 into modulus of minus 4, which is equal to plus 4 only. 4 by 2, that is 2. So A22 element, so which is equal to 2. So now again similarly A31 element finding. So third row, first column element by using the same condition. So now I is equal to 3 minus, here I is equal to 3 minus j is equal to 1, 3 into 1. So which is equal to 1 by 2 into 3 minus 3 is 0. So finally we get A31 element is equal to 0. A31 element is equal to 0. Similarly, finding A32 element. So now A32 is equal to, so I is equal to 3 here, j is equal to 2. So now substituting in this, so 3 minus, so 2 into, so sorry, 3 into j is 2. So that's why here 1 by 2 into, so 3 minus 6. So I is equal to 3, j is equal to 2. So that's why 3 minus 3 into 2. So which is equal to 1 by 2 into minus 3. So minus modulus of minus 3 is plus 3 only. So that's why here 3 2 is equal to. So 3 by 2 we get. So now therefore after finding the elements, so capital A is equal to, we have A11, A12, A21, A22, A31, A32. So now substitute the elements here. Already we have A11 element, that is 1, A12 element 5 by 2. So that's why 1 and 5 by 2. And here A21 element, that is 1 by 2. 1 by 2, A22 element, that is 2, and A31 element, that is 0, A32 element is 3 by 2. So see here, like this we can find the matrix A, so whose order is also here, first row, second row, third row, so 3 by 2 only. So like this we can construct the matrix A whose order is 3 by 2. See, the next question is find the cofactors of the elements 2 and minus 5 in the matrix. So we have to find the cofactors of 2 and minus 5 elements. For every element we can find the cofactor, but you take the let A is equal to the given matrix minus 1, 0, 5, 1, 2, minus 2, minus 4, minus 5, 3, see like this. Now to find the cofactor of, see here, cofactor of element 2, see 2 present, the element 2 present in the second row, second column. So which is equal to, so now determinant of, see second row, second column you delete, second row, second column. So in which only the element 2 presents, we get minus 1, 5 and minus 4, 3. Deleted second row, second column. Why? The element 2 presents in the second row, second column. So then, and also here, so while finding the cofactors of the elements, we consider that here the elements are plus, minus, plus, and here minus, here which is plus, and this is with minus, and here which is plus, so minus and plus. So why taking here plus, the element 2 presents in the second row, second column. Actually this is minor multiplied with minus 1 whole to the power of n. So here second row, second column means 2 plus 2. So we get minus 1 whole to the power of 2 plus 2. This 2 represents rows and 2 represents columns. So finally we get what here? Plus only. Minus 1 whole to the power of 4 is nothing but what? Plus. So that's why I consider here plus. So determinant of, so minus 1, 5, minus 4, 3, so which is equal to plus. So here determinant finding minus 3 and minus of minus 20. So which is equal to here, so plus minus 3 plus 20, so which is equal to 20 minus 3, that is 17. 17 is the cofactor of 2. So here plus 17, that is also. Why plus 17? The 2 presents in the second row, this represents the row and this represents the columns. So second row, second column, adding both of that, multiplying with, so minor multiplied with minus 1 whole to the power of second row, second column, adding of second row and second column, sum of second row, second column becomes plus. Otherwise you can take directly plus also. Similarly, finding the cofactor of minus 5. which is equal to, see here, minus 5 presents third row, second column. So third row, second column if you delete, so third row, second column, we get minus 1, 5, 1, minus 2. Minus 1, 5. So here 1 minus 2, 1 minus 2. See here, that is minor. Minor of minus 5 is determinant of minus 1, 5, 1 minus 2. Minus 1, 5, 1 minus 2. So how we get this is by deleting third row and second column. Third row, second column present minus 5. So third row, second column means minor is multiplied with minus 1 whole to the power of third row, second column. This represents rows and this is columns. So finally what we get here, minus 1 whole to the power of 5. So into determinant of minus 1, 5, 1 minus 2. So which is equal to, we get minus. So that's why I already kept here minus. Like this also directly you can take minus, or by applying like this also you can consider. So this is, so 2 minus 5, so which is equal to minus of minus 3, so which is equal to 3. So therefore finally we can write that, so cofactor of 2 which is equal to 17, and here cofactor of so minus 5 which is equal to 3. So like this we can find the cofactors of given elements.